Hey, what's up? So earlier this week, Arduino released a new product, a new board with the Uno form factor. This time it's the Uno Q. I think the previous one was Uno R4. Still the same form factor that we've had since day one, basically, of Arduino. So yeah, that board is called the Arduino Uno Q. Q as in Qualcomm, because they also happen to, they just got acquired by Qualcomm. The company Arduino got acquired by Qualcomm a few months after Edge Impulse, after Foundries. So some companies that do a lot of open source. So it'll be interesting to see how things develop over time. But this acquisition is not the topic of the video. I really want to spend some time talking about the Arduino Uno, what's there in terms of hardware, and maybe more importantly, software. I was lucky enough to get my hands on the device. It's only going to be available. People can order it today, and it will start shipping in a few weeks. So yeah, I did build some demos with it and played with it, especially in the context of Zephyr and Zephyr RTOS, because it happens to be featuring Zephyr, and that's kind of the topic of the video, showing a bit what's there. If you are familiar with Zephyr, you will basically learn what's going on there and sort of like the architecture. There's some really interesting bits. If you're not super familiar with Zephyr, but you are more like an Arduino person, you will hopefully also learn a few things about why it makes sense for you to have Zephyr under the hood, what it will enable, things like that. So hardware-wise, and I have a board set up with my demo. Hardware-wise, we have again like the Arduino Uno form factor, where I guess the main difference is that this time around it has, and we see it here, it has a microprocessor. It actually runs Linux, so that's kind of maybe a big move, a big change for Arduino. I mean, they did try that in the past with the Arduino Uno and others. But yeah, it has basically a Qualcomm microprocessor that runs Debian Linux. And it also has alongside it, it's kind of a dual brain architecture, like they call it. And so the other half of the brain, or the other brain, would be an STM32 U5 microcontroller. So looking at the specs real quick, you can see that, on one hand, you have this Qualcomm so-called Dragon Wing processor. That's kind of what you would have found in a smartphone a few years back, like a mid-range smartphone. It's really meant to be, effectively the board, I should have started with that. They market it as a single board computer. You have a USB-C connector, which you would usually use for power, but it is effectively a full-blown USB-C, which if you connect a USB hub, you can also attach a display, microphone, webcam, etc. But more importantly, really a display and a keyboard, and you get a computer. As of the release, in the initial release of the product, it's only the flavor that has 2 GB of memory that's going to be available, and followed by the 4 GB. So to be clear, and this is my own personal opinion, but this only 2 GB makes it quite slow in terms of like the desktop experience is not like the smoothest, but that's not necessarily the point. You have a desktop if you need it, but I would expect that lots of people would just SSH into the board or connect remotely into the board. But yeah, that's kind of digressing. That's still a really powerful processor, like in terms of video processing, and I guess you can see it here. It's really meant to do like video pipelines and so on, and you get the desktop experience as a bonus, I guess. And on the microcontroller side of things, and so the microprocessor, last thing, is it's quad-core CPU. And microcontroller is STM32U5, so effectively an ARM Cortex-M33, 2 megs of flash, and like 0.5 MB. I thought it was 0.5 meg, but 700 plus apparently kilobytes of RAM. So yeah, that's for the two the two cores. And the interesting thing is that those two cores, two brains, name them however you want, you can start writing code that targets either the really powerful microprocessor, potentially for running graphical, like having some kind of graphical user interface, or a web front end, run AI pipelines. That was kind of like a big buzzword as part of the announcement, doing like quote unquote edge AI scenarios. And so usually you would use Python there, and we'll talk a bit more about how this looks like in terms of like the developer development experience there, or on the Arduino, yeah, Arduino. On the microcontroller side of the Arduino, the historical way of doing Arduino, I guess, it's the good old sketches, right, that are written in C/C++. You might be familiar with that, right? Like the setup, loop, and like pretty straightforward language, I guess they call it. But I mean, effectively, this flavor of C++ where you're usually quite productive and start writing code that interacts with your sensors, etc., etc. And so, yeah, on the top of the board, the regular Arduino Uno shield, pinout, and connectors. So that's where you would connect basically any shield that you already have. As mentioned here, the microcontroller runs on top of the core, the Arduino core runs on top of the Zephyr. So those nice fancy abstraction that Arduino has had pretty much forever, right? To really easily toggle LEDs and like digital write, digital read on pins, do ADCs, do SPI, I2C, etc. This level of abstraction, this layer of abstraction, is called an Arduino core, and effectively they built that on top of Zephyr. So what does that mean? That means, well, one, that you can actually, even if you're not like an Arduino person, you can do plain Zephyr. Like the board itself, like the MCU side and MCU part of the board is something that you can just develop and start deploying your own custom firmwares based on plain Zephyr. At the time of recording this video, this is not like fully live just yet in the main Zephyr repo, but it will be imminently. There's a pull request, which is what we're looking at right now, that basically adds support for Arduino Uno Q in Zephyr, and you can start running virtually any application that's available in Zephyr. But more likely, what people want when they have the Arduino Uno, and it's an Arduino they want to use and develop using Arduino Core. And so whether you're going to use the good old Arduino IDE or what they call AppLab, which we will see in a minute, you effectively write code that targets the Arduino core based on Zephyr, which, by the way, everything is open source. And so this Arduino core, what is it effectively? Well, it's a firmware that allows to abstract all the peripherals of the device, of the Arduino device, like again I2C, GPIOs, and so on and so forth. And one thing that's interesting is that particular firmware, you don't rebuild it every time you need to deploy your own application, because actually, like that abstraction layer, it's pretty static. Like there's only you don't need to recompile all the abstraction layers for accessing SPI, etc. If the only thing you need to do is like, I don't know, blink an LED, that kind of stuff, right? So effectively, what they have is something they call a loader. So as you unbox your Arduino Uno Q, basically it already has I guess we could call it a bootloader, an existing firmware that's there, and that's based on Zephyr, that exposes and contains and implements all the Arduino APIs for, again, digital read, digital write, etc. But it also leverages, so we are looking at the code of this particular loader right now. It's again on GitHub, open source. It's a Zephyr app. And so one of the things this does, and we can actually look at what are some of the features enabled by this firmware. One that's really worth noting and that kind of makes sense is that built and baked into this firmware is the fact that it exposes and implements the Arduino core APIs, but it also has something interesting among the many features enabled, and obviously GPIO I2C SPI would be there too. It does have something called LLX. LLX is a feature in Zephyr, LLX for linkable loadable extensions, a feature that allows an existing running application to dynamically load and execute binary code that it wants to run. So in the case of the Arduino sort of like setup, and the way they've done it is that, again, you unbox your Uno Q. It's out of the box. It has already the Arduino core and loader built into it, and then you start using the Arduino IDE or the App Lab, which again we'll see in a minute, to build your own application. And this particular application is going to be like, I don't know, you blink an LED, you do a bunch of things. You build this particular application and only that code. And then using the IDE, you flash it to the board, but you only flash that. Like you don't erase or you don't change the bootloader. You really only load your own custom user code in a dedicated flash partition on the device, and then reboot, and then the Arduino, the loader that we are looking at right now, will on reboot realize that, hey, there is an Arduino sketch that's been put right there in this particular area of my flash storage that I knew could contain sketches, and so it will start running it. And we can actually see it. So there's a bunch of boilerplate code in the bootloader that will probably add a bit of noise. But as we scroll, and this would be where are we? Yeah, so somewhere along those lines, and in this particular area, we end up looking and accessing the partition in Flash that has the sketch. We load it, and then we execute the main function of the sketch, the main entry point. And effectively, in the context of Arduino, for some of you might have tried in the past to look at what's behind the setup and the loop for an Arduino sketch, but effectively, the main of the sketch is a function that first calls into setup and then does an infinite loop, calling the loop function over and over again. So that's what the Arduino, the way the Uno Q works. So for many people, this doesn't really change their life. I guess, like if you're just like, you use the Arduino IDE or the Arduino App Lab to build applications, the only thing it changes for you, but it's actually quite a big deal, is that it's much faster for you to build your sketches, because you don't recompile the complete and the entire core every time you build like a really simple, you have only a really simple change that you want to deploy, or you have a really small application. The core is already there, already flashed, already tested even by the Arduino team. So yeah, that doesn't change more than that. The fact that you get a slightly a faster build time and deployment times. But what's also interesting is that nothing prevents you to effectively use the Zephyr APIs should you want to, which is kind of interesting since basically, and I think we can look maybe at just random Arduino code here just for the sake of so that would be typically Arduino code, right? Like a blink LED sort of example. This is not using any Zephyr API whatsoever, and this is actually quite convenient for like basic demo scenarios. Or basic applications. You don't really want to think further the fact that, hey, there's a loop, it's going to be called indefinitely. So let's just write the code there. But then you start having applications that maybe get slightly more complex. Let's see about this guy. This guy, we can start seeing that maybe the sort of the flow of the application is maybe not as straightforward as it should be. You have a button. When you press on the button, you want to react to that by toggling the status and the state of an LED. This is also done in the infinite loop, in the super loop. Sure, why not? But typically in embedded development, you would want to do something where it's more like you have potentially like several threads that run in parallel. Like you have a thread that's responsible for monitoring your inputs, and other threads that are more reacting to that, and sort of like either using like semaphores or like other synchronization primitives, so that you really like move out of this super loop, which again is kind of nice and straightforward for really simple loops. But then when you have like an actual application with multiple things happening in parallel, you want to get threads and stuff like that. So long story short, now that the Arduino core is based on Zephyr, you can potentially use Zephyr APIs. And so that's what I did in the demo. Long intro, long segue into what I built as a demo for sort of showcasing what it means, what it brings to have Zephyr in the mix. So demo is there on my desk. The Arduino Uno Q is connected to a bunch of so-called Modulino sensors. So using a really convenient quick stemma connector, you can digit chain actually your sensors. You can see an LED strip and a bunch of LEDs that visualize something. Apparently, let's see what in just a moment. We have right here a thermometer and humidity sensor as well, and in fact, the third sensor on the right-hand side is actually a distance sensor. So as I move closer to my to the sensor, it starts turning red. Apparently, this means that something bad is happening potentially, or some kind of intrusion detection. So as you can see, a bunch of things are happening in parallel, right? And the whatever is happening when I get really close to the sensor. This is potentially something that's like safety critical, and you really don't want to miss like when something happens at this moment, and when potentially you start running really complex processing algorithms and whatever, this needs to work, right? And sure, you also want to try and acquire temperature and humidity at the same time, but maybe this is something that's slightly less important. Can you easily do that with a super loop? Not sure. It might be a challenge. You might have things that take time that will just sort of like mess up the loop entirely. It will be really hard to keep track of time, etc. So that demo, let's see how it was built. And let's move actually to the, let's open the Arduino, the so-called App Lab, which is something you can either, if you use the board as a single board computer, you can just hack directly on the device, or you can connect to it over USB, or in this case, actually, the board is not connected to the PC I'm using for recording, but nevertheless, it's connected to the same Wi-Fi network, so I can connect to it, this makes for actually a nice experience, I think. What can we see here? We can see some built-in examples that show that we could, I guess, deploy to give you a sense of what's going on there. I'm not sure this makes sense to do this particular but we could. Let's look at the code. I guess it will be a good way to set to sort of set the expectations with regards to how things typically work. An application in AppLab is usually you have those two brains on the board, the Linux MPU microprocessor and the STM32 MCU microcontroller. And so for the former, you would have Python, usually whatever code you want to run on the Linux host, you use Python. And for the MCU, this would be C code and C++ code, the good old sketches. So in this case, this is an application where this is Blinky, where it's kind of like maybe a weird way to do Blinky. And actually, you know what? I didn't plan on doing this, but let's do this. This will be, as always, you can skip to whatever time code if you think this part is boring. But yeah, let's launch the application in the background. Hopefully it will work. And then we'll see how, what this does. But basically, this is a kind of a convoluted Blinky just for the sake of showcasing what happens when you want to have the two brains doing two different things. On the Python side of things, it is effectively building a kind of web UI. And apparently, from the web UI, when I click on some kind of graphical widget, I'm calling into a so-called bridge. I'm calling an RPC, or I'm doing a remote procedure call, indicating someone somewhere that I want to set the LED state. As you have guessed, the RPC, the other endpoint in question, would be the Arduino sketch. So on the Arduino sketch, you have you use the Arduino router bridge library to effectively communicate over UART with the microprocessor, either calling methods or exposing methods for the Python code to call into. So the here I am telling, as I start my sketch, I am telling the Python script that if it wants, it can call a set LED state, and if it does, then it calls into the regular Arduino APIs. So apparently it wouldn't, the sample didn't work, but that's fine. I don't think I want to show you that anyways. Meanwhile, though, it kind of stopped and broke the actual demo that I wanted to show you, my custom Zephyr demo. So let's open it, and let's open it. Let's wait a bit for it to compile. While it compiling and deploying, while it does, we can have a look slightly further into not only, again, the fact that you have Python code on one hand and Sketch, C++ sketches on the other. A few other things that are going on. You have what they call bricks. So the bricks are effectively on the Python side of things. They have prepackaged a bunch of libraries for doing GUI, time series database, Edge AI with the Edge Impulse stuff, and I think a few other things. So basically, this is the manifest of my Python application, and so the application is now running. I want to actually show it in this browser. I think I'd rather show it here. Let's see. Oh, it is running. So that's cool. So not only it is doing things like physically, we could see that the sensors were apparently doing and reacting to me moving my hand, etc. But we can see that it is actually apparently being streamed in real time to the graphical user interface. So that is quite cool. If I get really close, not only the MCU instructs the LEDs to turn red, but apparently this also has an effect in the Python GUI. So let's look a bit at that part of the code. The sketch will be, and this is where the AppLab sometimes dies on me. So if you give me just a moment, I will start it again. I'm not trying to hide any dead bodies there. Like sometimes, I think I'm Something's wrong maybe with my network or something, but whatever, you will even get to see my password here. There we go. Real demos, no editing. Back to the demo. All right, so the code, yeah, I wanted to show you the main, like my sketch. Sure, I have a setup, but the loop doesn't seem to be doing anything. How come? How's that possible? Well, it turns out that I'm actually leveraging the fact that I can do Zephyr stuff to do things in different threads. So CPU monitoring, we will see in a moment, but things like dealing with the proximity detection / distance sensor, or dealing with the temperature and humidity sensor. This is something I do outside of the super loop, apparently. So the thermosensor, what's going on there? It is effectively using the Zephyr APIs to define a thread that has its own stack and that's responsible, and that's going to be also like it's statically defined and will automatically start, and possibly and certainly it's responsible to look at temperature and humidity and do something useful with it. So as I call the init method, I basically tell the thread that it's now ready to go. And what does that thread do? It does a loop, I guess, but its own loop. It's a completely different thread than the Arduino Sketch super loop. And so what it does is using the Modulino thermo APIs to get the temperature, the humidity, turn that into a string, and then send that string over the bridge. So over serial, over UART, it's being pushed to the Linux host so that the Python code can potentially do something useful with it. And that's, I guess, what we want to see. The Python code is using the Streamlit brick, which, by the way, is awesome. This is a library I had no idea existed until I worked on this. We can really briefly look at the Streamlit. It is actually really, really nice. It's an open source library that makes it really easy to do GUIs in pure Python. And so like you can create nice interactions, and you can have nice widgets and charts and whatnot in really just a few lines of code. And the library takes care of all the Ajax, I guess, all the automatically refreshing the data, etc. So it's quite nice, and that's what I've been using. And quickly skimming through the code, it's only, it's a few hundred lines of code, but most of it is just like styling and so on. The core, the main bits are really pretty straightforward. And so here, among other things, the Python code says that it exposes a sensor data RPC, which the sketch, the C code, can potentially call. And when it does, when the sketch, as we saw just before, sends the sensor data separated with pipes and spaces and whatnot, we parse it and we put it in some kind of a data buffer that's then used in our GUI sort of like refresh loop. This is where it looks at the sensor data. If it has known names, it shows them at nice widgets. And so that's what's going on for the temperature and the humidity. If we go back to the sketch, there was the proximity detection as well. As you remember, getting my hand closer to the sensor, we see that it's turning red. How come? Like, what's going on there? Same as before, we have a thread that's statically defined that does all things proximity detection. As we init this module, we then unlock and tell the thread that it's ready to go. And that thread, again, has its own infinite loop where it pulls data and gets data from the sensor, does a bunch of like smoothing and anti-aliasing and whatever so that the view meter is slightly nicer to look at. But effectively, at some point, it decides based on the distance whether if we are below 12 centimeters, it starts turning yellow. If we're below 7, then it's effectively red. Don't mind the naming. I guess it's confusing, but that's what it is. When we are really too getting too close, it's turning red. But one more thing that it's actually doing is that I am sort of pretending I wrote some code that, and this is almost the first time we see that, if not for the semaphores before, but this is using Zephyr APIs right from the sketch for doing something which is in this thread, in the proximity detection thread, I'm going to pretend that I'm doing something really important and that I'm going to be busy for 3 full microseconds. So that basically, so as to illustrate that whenever the proximity detection thread gets really busy, it doesn't necessarily mean that the rest of the world collapses, and quite the opposite actually. So if we go to our web GUI, go back to here, we can see that it's working. We saw that before, and I could also like warm up the temperature sensor, I guess. Let's see, yeah, and my finger is moist too, it would seem. But what else is going on? This guy right here, and I think this guy is going to be really interesting to look at. There is another thread that's working, and that as part of the initialization, I've been also launching CPU monitor init, and this one guy is basically a thread that not a thread actually. It's a module that exposes three methods. Well, sorry, I'm confused. Sorry, one here. Got distracted for a bit. The CPU monitor exposes the get CPU stats method, which when called is basically using some Zephyr APIs and Zephyr thread monitoring APIs to gather and to compute CPU cycles used by all the threads that are running on the system. And so here the UI every 500 milliseconds or so remotely calls the get CPU stats method from the sketch, which in return gives the list of all the threads currently running and their CPU usage. So we can see them here. Some of them threads like thermosensor proximity detection, those are mine and I created those. You can see that there's also a few others that are there because it's just Zephyr under the hood. And the green thread main is effectively the main sketch, which sits idle basically because it does nothing. And one thing that I think you are expecting by now, or kind of see it coming, is that if I get my hand really close and I start triggering basically the proximity detection / intrusion on the device, we can see that the device gets really busy, or at least busy-ish. The proximity detection task, it's 16% of the CPU cycles. But meanwhile, we can still monitor the temperature. We can see do the CPU monitoring, etc. So that's actually quite nice, right? And so what else I wanted to show? But basically the fact that LLX also allows me to, like on the fly, I could deploy new applications. And this is where I like to call this basically Zephyr sort of becoming just like Docker, sort of. You can start deploying containers with LLX. You have potentially, you package your sketch or your application as an ELF file, a binary that can then be dynamically loaded at runtime. I wrote, and this is where I got confused just before, I wrote another module. And the LLX loader, CBP and H files, they contain and they define 3 RPCs that allow, and everything's on GitHub, so I will be certainly sharing the link so that people can have a look. This expose methods so that one can upload a binary to the board and then load the binary. Similar to the built-in Arduino core loader that we saw before, it creates a new thread and starts running the thread, which means that if I go back here, open and say that, hey, you know what, I want to deploy, and let me just zoom back just a little bit so that we see everything. So yeah, the binary is ready to upload. I'm not doing it just yet because I want to make sure that I show you that as it is uploading, and it still isn't, but as it is uploading, we will be able to still trigger the really like safety critical, really important proximity detection algorithm while the board is still doing something else that's potentially quite resource intensive as well, but it doesn't matter. We have all those threads with all their own priorities, and the Zephyr scheduler taking care of having everything working in parallel. So let's click on the button, and I'm going to zoom down one tick less. So just pay close attention to what's going to be happening in terms of CPU utilization, but because the bridge is getting really busy because it was doing some transfer, but I was also able to do some proximity detection. You didn't see the view matter like getting stuck or anything. It was there the entire time. And did you notice something else that's new? Yes, that's this guy here. The LED is running. And do you notice something else that's new? Possibly the new thread and process that we have running. It has an unfortunate color scheme that was picked up. So this one right here, this is definitely the bridge. The pinkish is the bridge, and blink is, I guess, buried somewhere at the very bottom right here. I might even be able to make it show up if I zoom up. Let's see. But yeah, blink is a new process. I could also I could deploy additional sketches that would just work. I mean, until I run out of memory, possibly. But that's basically the kind of things that you can do when you start using, like you can combine basically the Arduino APIs that you love and that are usually, quite frankly, really nice and really convenient to use for doing things like, as we saw right here, like doing things like interacting with the temperature sensors, etc. Like I wouldn't necessarily want to use the Zephyr APIs here. Like it's just so convenient, right, to do it this way. But if I want to do things that have to do with the scheduler and accessing like kernel primitives and kernel objects, it's nice to be able to do so. There is just a really small caveat, which is that not necessarily all APIs might be available out of the box. Because remember, like all that everything that I've shown right here is effectively being deployed on top of the existing firmware, existing Arduino core that's already there on my Uno Q. So that core needs to contain those APIs that I want to use. Otherwise, it just doesn't work. It needs to expose them to me for me to use them. And so as part of the README of my demo, I actually show some of the things that I am basically utilizing some APIs that wouldn't be there by default. But luckily, it's really easy to build your own Arduino core if you want to be like do the kind of things that I've been doing. You basically just tell LLX that it should expose some of the APIs that you plan on using, and then they're available for you to use. So with that, I think this is what I had. So I think this is quite interesting that, frankly, like everything is open source. If you want to use the Arduino App Lab, don't want to think about Zephyr at all, don't. But if you want to start being able to leverage all the scheduling capabilities, etc., it's there for you to use, either from App Lab, either from the desktop Arduino IDE, or from, as I said in the very beginning, or you can also just like completely get rid of the Arduino core and just do like plain pure Zephyr development. That works too. And so yeah, that kind of gives you both a learning curve, like if you want to get more familiar with Zephyr, that's kind of like the way you would do it. Start with just plain Arduino and then start sprinkling some Zephyr APIs. But it also gives you options, right? Like that's, I think, the beauty of open source. So with that, please share in the comments any questions you have. Check out the GitHub repo, and really looking forward to see more iterations on this and where this will be going. But I think this is an interesting architecture. Curious to see what you guys think.